Great, thanks, Heather. Hey, good afternoon, good morning, good evening to everybody, depending on what part of the world you're joining us from. As Heather said, my name is Ron Lowry. I'm the Eastern Area Manager for Hazard Control Technologies, and also a fire chief. I've got 38 years in the fire service. I'm a fire chief with the department in Allegheny County, Pennsylvania. So today's presentation, we want to kind of go over what encapsulator technology is, and then we'll look at the various classes of fires and how an encapsulating agent can actually help you with some of these new high hazard fires that we're dealing with today. So a little bit about the company first. Here at Hazard Control, it's our mission to encapsulate the world. We would like to make it a safer place through leadership in fire prevention and protection, utilizing a fluorine-free, eco-friendly, innovative encapsulator technology. Hazard Control, we're headquartered in Fayetteville, Georgia, just outside of Atlanta. All of the agent is manufactured at our facilities there in Atlanta, but we have a global distribution network and a global reach. So it's a US made product that's used worldwide. So again, the topic for today for this webinar is, fire service solutions using encapsulator technology. So as we know, we have ever evolving hazards coming out in the fire service, and it seems more and more every day, from the use of synthetic materials now within our carpeting, upholstery, the general things we're finding in our home, to the amount of Class D metals that are now located inside of vehicles. Some of the numbers I've seen is the newer vehicles, 2017, 2018 or newer, you could have up to 250, 300 pounds of Class D metals of various makeups, either magnesium or other exotic Class D alloys within that vehicle. Solar panels, lithium-ion batteries seem to be leading the way, as far as the next great challenge that is facing the fire service today. And we're going to, as I said, look as we go through how an encapsulator agent can actually help you handle these hazards that there really isn't a good all-around solution for. Maybe individual products can handle individual hazards, but nothing that can really handle all of them simultaneously outside of an encapsulating agent. So real quick video here, just kind of looking at these new hazards that we're facing today, even in that basic structure fire environment. So I'm sure this is a video a lot of folks have seen before. It's the 1960s, 1970s room versus modern furnishings, and what those synthetics do being in that the environment that we're dealing with today. So you have the natural fibers here on the left, your cottons, your solid woods. Again, took a little longer for that fire to grow in intensity, probably cotton drapes. So again, all natural fibers, don't really produce a whole lot of smoke, and really take an extended period of time to get going compared to the newer synthetic materials. So as you can see already, that heavy toxic smoke being generated by those synthetic materials, higher heat ratings, quicker time to flash over, all of these direct hazards that are facing both the fire service and the general public. The time we have to get out of a building, the time we have until we're facing flashover is literally dropping by the day. So as you can see, the heavy black smoke, we have the fire free venting. Room went to flashover in 5 minutes, compared to, again, a very slow moving, very slow growing fire with a natural material. So again, the high hazards we face today are much different than what we faced even 10, 15 years ago. So I guess the real question is, what's your department currently utilizing to fight today's high hazard fires? And is it sufficient to handle all the hazards you're going to face? So let's look at an encapsulator agent and what are they? So an encapsulating agent, it's an innovative fluorine-free, non-corrosive, biodegradable agent, multi-UL listed for Class A and Class B fire suppression, and can also be used for flammable liquid spill control. Kind of a textbook definition for an encapsulator agent. It is a water additive whose basic building block is a spherical micelle. You're going to hear me talking a lot today about that micelle because it's the building block of an encapsulator. It's what's going to make it work. So those micelles are capable of encapsulating both carbon molecules as well as polar and non-polar hydrocarbons in both the liquid and the vapor state, chemically, molecularly bonding onto that hydrocarbon to render it non-flammable. So we have an animation here that's going to kind of go over what an encapsulator agent is and what happens when it mixes with water.
Encapsulator Technology, the next generation of fire and hazard mitigation. First, we start with a simplified version of a single encapsulator agent molecule consisting of a hydrophilic polar head which loves water, dissolves in water, and a hydrophobic nonpolar tail which fears water and will do anything to get away from water. Once the EA molecules enter the water, they instantaneously and automatically orient with the nonpolar tails inward and the polar heads outward, forming millions of spherical micelles. Micelles travel towards and exit the nozzles, forming EA droplets. Micelles nearest to the surface of each droplet automatically break apart. The nonpolar tails orient outside the droplet with polar heads on the surface, forming an EA skin on the surface of every droplet. In addition to the EA skin, there are millions of molecular spherical micelles within each droplet.
So the orientation of the agent, both on the surface of the water droplet and within the water itself, gives you three unique features that make the agent as efficient as it is at suppressing various classes of fires. And we're actually, through the next few slides, we'll break each of those unique features down individually. So if we talk about the fire tetrahedron, we need to remove one leg to suppress a fire. And generally, most fire suppressing agents will work on one leg of the tetrahedron at the time. You know, whether we're using water to remove heat, whether we're using a foam to try and create a blanket to manually separate the fuel from the oxygen, whether you're using some type of an inerting gas like the CO2 or a Novak to displace the oxygen, or even a CO or a dry chemical extinguisher, a powder extinguisher, an ABC to interrupt that chain reaction. But each of them working on one leg of the tetrahedron at a time. With an encapsulating agent, we get multi-class suppression capabilities, you know, A, B, D, the lithium-ion batteries. And they do that, again, through the unique features of one, encapsulation. So that encapsulating agent can actually bind onto that hydrocarbon molecule. That's tested through this NFPA 18A section 7.7 spherical micelle stability test. So this test protocol actually is a test protocol to show if your agent creates spherical micelles and if those micelles are capable of encapsulating hydrocarbons and maintaining that encapsulation in the presence of high heat. So for that test protocol, we take one part of an encapsulating agent here. It's F500, 8 parts fuel, and mix that in with 40 parts water to make a solution that is then non-flammable, non-explosive. So that test protocol with hazard control, we take a gallon of gasoline, mix in 16 ounces of the F500 or our other encapsulating agents, and then mix in 5 gallons of water. What the test calls for is after a minute, a torch needs to be able to be passed across the entire surface of the solution without having ignition. And then you have to leave that solution sit for 2 hours. And again, be able to pass a torch across the surface without having ignition of that fuel. What we're showing is that we have a stable micelle capable of encapsulating that fuel, and that encapsulation is long-term in the presence of high heat, that the encapsulation doesn't break down. So when we're talking the fire service, not really a way we would typically use an encapsulator when you think about it, the test protocol. I think this video kind of drives home the point what an encapsulating agent can do for you. So imagine your department just responded out on a motor vehicle accident. You have fuel on the highway, but yet you have to make an extrication out of that vehicle. In most cases, we're going to pull a safety line and, for the most part, keep our fingers crossed that we don't have a spark or that something happens that we end up with a flash fire, potentially injuring the patient and our members. So what you're going to see here with this video, we're going to be pouring out some gasoline. So there's your gas spill you would run into at a motor vehicle accident. We'll now take an extinguisher with 10 ounces of F500 added into it, which gives you that 3% solution. So we're going to go ahead and encapsulate the center portion of that spill. So that fuel now is locked up inside of that micelle, rendering it non-flammable. Firefighter's going to take a torch and ignite the fuel that was not treated. As you can see, the unencapsulated fuel doesn't burn. He'll go a step further and light the fuel on the opposite side of the encapsulated fuel. So even with direct flame impingement, you can see, even in the presence of high heat, that encapsulation doesn't break down. So take the extinguisher, finish extinguishing that fire, suppressing the fire. So not only treating the fuel, rendering it non-flammable, but suppressing that Class B fire. He'll now take a torch and actually show that that fuel that's now been extinguished, just like the fuel in the center, is encapsulated. So in the scenario we were talking about at the beginning with that vehicle accident, you would have the ability to render that fuel non-flammable before you started an extrication, removing that possibility of a flash fire for your members. So treat that fuel spill, use your 4-gas meter, run it across the surface of the spill. If you have 0 LELs, you know your fuel's encapsulated, you've rendered it inert, and you now have a safe working environment. Next feature is that rapid cooling. So the agent has the ability to absorb heat as opposed to generating superheated steam. So how it does that is those polar heads on the surface of the skin of F500 on the outside of the water droplet actually work like a heat sink. They absorb that heat and then rapidly transfer that heat energy to the polar heads of the spherical micelles within the water droplet. So that happens through thermal conveyance. It's conveying that thermal heat from the surface F500 skin into the micelles within the water droplet. Really good video to drive that point home. We take this from some training we did with the New York, New Jersey Port Authority, the guys that are protecting the Lincoln Tunnel, the Holland Tunnel, some of the bridges up in the greater New York, New Jersey area. So this was testing they did at their training academy. We have a fully involved vehicle fire. We're using a pre-mixed solution of F500 with about a 20-30 gallon per minute nozzle off their truck. As you can see, rapid cooling of the fire. You can also notice another great feature of the agent, where that heavy black smoke that we generally get off of those burning synthetics pretty much disappears almost instantaneously. So not only rapidly cooling that fire, but also improving that IDLH atmosphere. Another video here with the car fire. This one, we're just going to look at some of the thermal imaging. So another vehicle fire. This one's going to be extinguished with our TKO nozzle. So a 20-gallon per minute nozzle. As you can see, again, very rapid extinguishment of the fire. As the firefighter continues to hit that hot spot, you can see how rapidly that steel, that metal from inside the vehicle is cooled. So again, much more rapid, much greater cooling ability than what you would see with plain water with, again, a very low flow. So if you look at that total vehicle fire, we haven't probably even gone with a total application rate of 30 seconds. So that vehicle was extinguished with about a 10-gallon solution. Next unique feature, in my opinion, probably one of the most important aspects of the agent when we're talking about safety for firefighters and even the general public, is this interruption of vapor phase combustion, which gives us the ability to drastically improve the air quality and drop the toxins that are within the smoke that's being generated from the fire. So the first test we have about the ability of the agent comes from Clemson University. This was a study that was done in the late 90s. In this particular lab experiment, they were burning toluene. They did multiple burns where they sprayed a plain water mist through the smoke column. And then they did a subsequent burns where they sprayed a 3% solution of F500 through the smoke column. During the testing, they were looking for things like how dense was the smoke. So they were shooting a light beam through the smoke to see what the density and the opacity of the smoke was. They looked at the soot accumulation inside the funnel to try and gauge how much soot was actually generated by the burning toluene. And then the last thing they looked at was the soot and the smoke toxicity. After the testing, when they compared the results, they found that when the F500 was used, that the soot was decreased by 97%. The toxic smoke was reduced. The toxins in the smoke were reduced by over 98%, and the visibility was increased by 68%. Here's just one of the test results of some of the toxins that were actually reduced within that smoke when the agent was used. So again, those nasty benzenes, the fluorines, some of those other dioxanes that we know are the cancer-causing toxins that firefighters are facing on a daily basis. The conclusion from that Clemson study is this information, along with vapor reduction experiments, suggest an interruption of vapor phase combustion, possibly inhibiting the radical coalescence into soot particles. So when we kind of explain this to folks and everybody kind of glazes over, trying to wrap their head around what does that really mean. So an analogy I like to use is when we talk about why this is happening, it has a lot to do with the cooling capabilities of the agent actually taking some of that energy, that free radical, the energy out of the free radicals, so we get to slow them down. But more importantly, the F500 molecule is a much denser molecule than plain water. So just like a ball traveling through the air can travel great distances and with ease because the air that we're breathing isn't a dense substance, so can those free radicals easily pass through an H2O molecule. But if you reverse that and again try to throw that ball underwater, that ball doesn't travel through that water because the water is so much denser than the air. It doesn't allow that ball to go through. The water actually absorbs the energy and won't allow the ball to travel. Same principle. those free radicals easily travel through that water molecule, but they can't travel through the F500 molecule. So that therefore we stop them from coalescing, from coming together and forming that soot and smoke. So that testing, as I said, was done in the late 90s. I know I've personally been getting a lot of questions from the fire service. You know, the testing's great, but it's a lab test, and do you have anything a little more recent? This past summer, the Laval Fire Department in Canada, they've been an F500 user, but they were looking for two things. One, how could they make things safer for their members? And secondly, they wanted to show to their municipal government that making a switch to a product, a complete switch over to a product, was actually going to be beneficial. So they staged some controlled burns where they were using plain water for one of the burns and then a 1% solution on the other burn. So in between each of these burns, they actually were using brand new, they swapped out their hoods. So brand new Nomex hoods between every burn. And they even changed the inner liners of their helmets. So they did 2 burns, fire 1 and fire 2 were what I would call event limited fires. So much more smoke built up inside the building, not a whole lot of ventilation. But they did, again, a fire either way, that way. Then they did 2 more of a vented free burning fire for fires 3 and 4. Again, one with plain water, one with F500 with a 1% solution of F500. Some of the things that came out of that testing from the firefighters that were on scene is, again, the use from day one could have minimized the amount of water used, the production of smoke, and the number of hours worked by firefighters, based off of how much more rapidly they were able to suppress the fires with a lot less water and a lot less hours. And again, but above all, its use from day one could have prevented the inhalation of carcinogenic fumes by our personnel. The conclusion that came out of this study, and I like to, generally when I'm in a room full of firefighters, I'll ask them and I'll put it out, not looking for answers. But when's the last time we've ever got 30 firefighters in a group to agree to anything? They had 30 firefighters that formed this committee, and the conclusion that came out of that committee from all 30 firefighters is that they were going to move forward with the use of an encapsulating agent to prevent cancer in the Laval firefighters. What drove them to that conclusion was the evaluation of the hoods. So those hoods were given to the University of Ottawa to perform testing on. When the University of Ottawa compared the toxic load within those hoods for some of the VOCs and the aromatic hydrocarbons that were in there, they found drastic reductions in the amounts for the hoods that were worn when the F500 was used. So as you can see on the vent limited fire, 71%, 83%, 60, 63, 83, 89, 90. Now, not as drastic or reductions on the free burning fires, but again, we didn't have the volumes of smoke because that fire was well vented. But again, drastic, serious reductions in the amount of toxins that those firefighters were exposed to during that firefight. So a really good video here I'd like to show that'll actually, let me get this minimized here completely. There we go. To show what we're talking about with that interruption of vapor phase combustion. So as you can see, we have 5 burning tires, heavy black toxic smoke. So I draw your attention to the smoke. Just keep your eyes on that heavy black smoke. We're going to be using a 1% solution of F500. As you see, your tires are still burning, but we're not generating that heavy black toxic smoke. That's what we can do by stopping that free radical coalescence. We can stop those toxins, stop that soot from forming in the smoke, and improve that IDLH atmosphere. So now that we've kind of gone over all of the capabilities of the agent and what it brings to the table, let's look at some of these fire hazards that we're facing and the various classes of fires and how the agent can work on those multiple classes of fires. So that first, let's just talk about basic Class A fires, you know, what we're facing every day: structure fires, dumpster fires, vehicles, those kind of things. So another vehicle fire here. Again, they're gonna be using the TKO nozzle. Again, only a 20 gallon per minute flow. So two things to watch here, some things to keep in mind. Look at the column of smoke, the header that's coming off of that vehicle fire. That heavy black toxic smoke. Watch as soon as the agent's applied. Look how rapidly that heavy black smoke dissipates. We have that white vapor, a little bit of gray, but almost instantaneously the black smoke goes away. Very rapid suppression of that vehicle fire. Two things to notice here. So when we're talking application technique, we don't need to flood that vehicle out. He's judiciously using the agent and the water, now just doing some basic overhauling. Hitting some of the smaller material that's still burning inside the vehicle, but again, not flowing those high quantities, those high volumes of water. Again, if you look at the bottle, so that's a self-adducting nozzle, pulling the agent right out of the bottle. There's very little agent being used out of that bottle. He's probably going to suppress that entire vehicle fire with maybe an eighth or a quarter of that half a gallon of agent that's in the bottle. So again, very little solution needed, very little water needed, less runoff, which means less toxins getting into the environment, even from the runoff that are coming from that vehicle fire. Again, rapid cooling, rapid extinguishment, very little solution needed. Look at some other testing here. This was actually done just outside of Toledo, Ohio. We were at the Maumee Fire Training Academy. We're doing some interior burns here. We're pre-mixed in the booster tank of their engine at 0.5%. I'll go ahead and turn the volume up here. You can actually listen to the firefighter talking about the temperature. So again, we went from 1,200 degrees at the base of the fire to 400, from 1,000 at the ceiling to 250 degrees. The agent works better. So in that particular scenario, we were using a smoothbore nozzle. The agent works better with a combination nozzle. So we're doing some burns here now in the evening. Same building, same apparatus. We're still pre-mixed at 0.5%. The only difference here is we changed the nozzle.
You guys had about 1,000, so you want to go? You want to hit and run?
See, that lower stuff doesn't look like it's burning.
Yeah. That's stuff that from this morning.
Go down on that lower stuff.
300.
That's probably just coming from the straw.
Yeah.
That lower stuff's not burning.
About 230 at the bottom and 930 at the.
So I don't know if you picked that up. We built that fire on top of the fire that we had previously burned that morning. So remember in the morning burn, we had fires, the temperatures at the base of the fire at 1200 degrees. The fire we have burning now is only burning at between 250 and 300 degrees at the base of the fire. They're theorizing that it's just the straw, some of the drier materials that we were using to get that fire started again. So the pallets themselves that were actually pre-treated from being extinguished in the morning wouldn't burn. So we weren't getting the heat generation at the base of the fire like we were at the morning, but we still had temperatures upwards of 930 to 970 degrees at the ceiling.
That's it. I got 975 now. I was inside.
932 at the top and about 300 at the bottom.
So you notice that we said earlier that you're not going to generate superheated steam with F500. So as anybody that's been in a fire service in a while, when you see a cloud like this coming out at you, you know generally it's pretty hot. You're gonna really feel it. The gentleman, right or wrong, that was with this thermal imaging camera is just wearing a job shirt. So again, if this was 212 degrees superheated steam, at this point, we probably would have been transporting him to the hospital.
113. Yep.
So we've now dropped those temperatures to 113 degrees at the ceiling. So we went from almost 1,000 degrees, 930 on the one tick, 970 on the other, to 113 degrees. In the hallway, he's checking the temperature from the outside. He's got 75. Firefighter came from interior and said at the ceiling in the hallway, they're at about 115, 120. So again, drastic reduction in heat, even though it's a block burn building. 1,000-degree temperatures, we gave it a pretty good pre-burn. You're going to see here in a second, I'll walk right past the material that was just burning. It's literally cool enough that you can be upright inside of that burn building without feeling that heat driving you down to the floor. So this video actually comes from us from Panama. This was a tire fire at a tire recycling facility in Panama. The good thing about this, we actually have a report from the fire chief that was, the incident commander on this incident, comparing it to a fire they had previously where they used plain water on it. You'll see some of those facts comparing the two incidents here as the video plays on. So again, with plain water, took them about 42 hours to extinguish it as opposed to 2 hours with F500. 2 apparatus versus 1. Notice that heavy black smoke's not being generated. With plain water, they had about 10 firefighters on scene. With this, they had 2. Total operating hours for the equipment, 84 versus 2. Again, the amount of heat that the F500 is able to absorb. There's the big difference, water consumption, 42,000 gallons versus 3,000. So in a rural setting where you're trucking your water in, you're literally using 1 tender instead of a water shuttle. So again, not just the reduction in soot, but again, even overall environmental savings, less diesel fuel, less chance of accidents on the road with those trucks running back and forth on the tanker shuttle. Not just a safety benefit from the fire, but again, great safety benefits overall. Another video that comes from Laval. So they did 2 additional burns where they were just doing exterior firefights. So something I want to draw your attention to, they have a drone up here where they're going to be recording the entire incident with the drone. So you're going to see they're going to pre-treat the exterior of the building here, just hitting the eave to try and keep that fire from getting up into the eave, up into the roof area of the building. So at least in the volunteer service, depending on manpower issues, particularly in rural applications or rural firefighting, we have to do a lot of transitional attack because maybe we don't have enough manpower on scene to initially go interior with the first couple people that we're showing up with. We don't have our 2 in, 2 out. We can't, it's not a safe work environment. So all we can do is try and do what we can do from the exterior. In some instances, we want to try and darken that fire down from the exterior to make it easier on our guys to get to the seat of the fire more rapidly and get that fire extinguished. We want to reset that fire before we open the doors and feed it more oxygen and make the fire worse. So you're going to see here, they're going to apply a stream from the exterior, not real long, maybe 7-8 seconds through the window. I just want you to pay attention to the smoke conditions for about the next minute after they have applied the solution through the window. So again, they're using a 1% solution of F500. It's kind of what we recommend for Class A fires is a 0.5 to 1%. So they're going with a 1% solution. So as I stated, not a real extensive application of the agent. Just watch the smoke. So initially, the first time I saw the video, I thought they still had a good fire up into the eaves. Looking at it, I thought, even though they pre-treated, maybe they had a good fire in the eaves. I'm thinking they thought the same thing the way they're applying back to the eaves here from the exterior. But again, watch how rapidly the conditions are going to improve in the interior. We talk about stopping that formation of the smoke and the toxins in the smoke. The agent's continuing to do that. Even though it's not still being applied, it's actually improving those interior conditions. The fire's not extinguished. You're going to see it here over the course of probably the next minute as the fire is going to build back up. But look how rapidly the conditions have improved. Smoke conditions are diminished. I guarantee you can't see the fire, so the heat's knocked down compared to what it was when they started the application. So if you are doing that transitional attack, it's drastic. It gives you the ability to drastically get to that seat of the fire without worrying about the flow path, without worrying about feeding that fire all the excess oxygen from that door being open. Again, the fire builds back up. They're going to go ahead, let it burn, and then continue the extinguishment a second time. But again, the ability to drastically improve that IDLH. Again, here you can see now that the fire is completely extinguished. You can kind of tell how slow the volume of that vapor is that's coming out of that third floor. So we talk about the wildland hazards and the ability of the agent to help, again, in that wildland scenario. So these come to us from a lot of the video, and some of the other things we're going to see here is from down in the Amazon back in 2018, 2019, with a lot of the fires they had down in the Amazon. the agent was used on quite a bit of that area down here. So here you can see they're making a fire break through this heavy timber. As you're going to see, as soon as the fire comes up to that fire break, rapidly slows the progress of that fire down, actually inhibits that material from burning. So what we're seeing here is some testing what we have that shows the increase in heat absorption of a water droplet when the encapsulating agent is added to it. There's another, you know, we saw a lot of the I'll call it the hand crew applications. This is from Argentina. Here you're going to see an airdrop. Again, how rapidly with the airdrop the fire is actually suppressed. We actually did similar testing this past, well, 2 summers ago with the Georgia Forestry Division. Georgia Forestry has now gone with F500 for their aircraft firefighting. So to my knowledge, that's the first state wildland crews that have completely adopted F500 for their aircraft firefighting is the state of Georgia now. So let's look at some of these Class B applications, things like gasoline, ethanol, diesels, and oils. Let's talk about application techniques. So we know normally with a Class B fuel, if we're using a foam, we only have 3 application techniques. We either need to roll it on, we need to bank it on, or we need to rain it down. So this is E85 gasoline. We're going to be using a 125 gallon per minute nozzle, 3% solution of F500. That's our recommendation for Class B fires is 3%. Notice the application technique. We're going to be using probably a 15 to 20 degree dispersed pattern, sweeping across the surface of the fire. So remember from the beginning, we talked about an encapsulator having the ability to encapsulate flammable vapors. Well, that's what's actually burning here. That liquid fuel isn't burning. It's heated up and vaporizing. The vapors that are coming off of the fuel are actually what's burning. So what we're going to do here is encapsulate those vapors that are burning, removing that fuel while simultaneously cooling the steel and lowering the temperature of the fuel to slow that vaporization process. So you'll see fire is extinguished. Now it's just some additional cooling on the steel to pull that heat out of the steel. So normally with a foam, we need to maintain that foam blanket for at least 15 minutes because all of that steel is still super hot. That surrounding substructure that's protecting the fuel is hot. And if the foam blanket breaks down because it's above the auto ignition temperature of the fuel, you can have another fire. The fire can reignite. As you're going to see here, I'll walk up to the tank. You can put your bare hand on the outside of the tank. That steel is now down to ambient air temperature. It's below the auto ignition temperature of the fuel. That threat of auto ignition is gone. So another fire here, this one with diesel, another 2-dimensional diesel fire. Same type of application we're going to see here. Going to give you a better because it's not in the middle of the night. you're going to see here that probably 20-degree dispersed pattern. You'll see the rapid sweeping motion. We're trying to cover as much of the surface area of that pit as possible so we can encapsulate those vapors that are coming off the pit. So again, rapid sweeping motion. It's kind of, you know, a wide enough pattern that we can cover a wider width, but we also need to reach to get across the entire length of the pit so that we can encapsulate all those vapors. So again, rapid suppression, rapid knockdown, again, encapsulate the vapors, cool that surrounding structure, the pipes that are coming up through, the obstructions that are coming up in the middle of the pit, as well as the ring of the pit. Take that heat away, take that threat of auto ignition away. So we talk about a three-dimensional fire, and what is that? So that's fuel that's burning from an upper plane to a lower plane. We think mainly in the fire service about tank truck fires. That's probably the most common three-dimensional Class B fire we face. But again, if you're in an area here like Western Pennsylvania where we have a lot of Marcellus gas well drilling, you know, we have had some wellhead fires, as well as if you have some refineries, that type of thing in your area, you may have distillation columns. That seems to be one of the more common fires at a refinery, is a fire within that distillation column. So again, all three-dimensional fires. And if we look at the foam annex and NFPA 11, it'll actually tell you that that foam is not suitable for a three-dimensional flowing liquid fire or for a gas fire. And why? Because if that is a three-dimensional object, you can't form a blanket over it. If the liquid is flowing, it's going to run out from underneath the foam blanket. So it really isn't effective. So we see here that distillation column fire that we were just talking about. This was actually done over in China with some gasoline. So this is a pressurized flowing gasoline fire. Again, single hand line, 3% F500. You're going to see here, he's going to break the thermal column. He'll actually encapsulate the fuel right where it's coming out. So you still had fuel burning off to the right, but he encapsulated that fuel and cut off the supply of flammable fuel coming out. The fire that was burning to the right extinguished itself. This next video comes to us from our distributors in Vietnam. So they actually built a tank truck simulator that it's flowing a mixture of gasoline and diesel down the side of the tank. So they started a flowing fuel fire out of the tank, and then there's going to be a pool fire below the truck itself. So they give the fire a pretty good pre-burn. Speed it up here so we're not just watching the truck burn. So we have better than a minute and a half pre-burn, almost probably 2 minutes by the time they start attacking the truck. So you'll notice the firefighter from the front of the truck, they're going to be using 2 3/4 hand lines. This firefighter is using it's a version of a cellar nozzle. So it's a very fine droplet rotating fog nozzle. So said earlier, we talk about droplet size. The smaller droplet we can get with an encapsulating agent, the more cooling and the more encapsulation capabilities the agent has. So as you can see, even with this large truck fire, we're using 2 hand lines, one on the rear, one on the front. Again, very rapid suppression of the fire. Fire is now actually extinguished. Again, continue to apply to cool that steel, encapsulate the fuel that's still running down the side of the tank to render that fuel non-flammable while we're cooling the steel, taking that auto ignition threat away. So again, rapid cooling, rapid extinguishment. Let's look at some Class D hazards, things like magnesium, titanium, zirconium. We talked about those vehicle fires, and to me, that's one of the most, it's an everyday fire for firefighters that we don't really give a lot of attention to. But if you think about it, it's probably one of the most dangerous incidents we're responding to. One, we're operating in a high hazard traffic environment normally, but even more so than that, we absolutely don't have any idea what's burning, especially in today's world. Is it a fully electric vehicle? Is it a hybrid? Is it running gasoline? Is it running E10 or E85? Is it running diesel fuel? Is the Class D metal involved? And if so, how much? All kind of questions that we really need answered. But a lot of times it's a guessing game, and we don't find out until it's too late. And unfortunately,
Everybody all right?
this is what can happen when it's too late. So this is actually a titanium recycler out in Los Angeles. So it's actually one of the companies based here in Pittsburgh. It's one of our customers. They have the titanium stored. So there's titanium turnings and chips that are stored in this warehouse. That's what's burning. Unfortunately, the firefighters are attempting to use water to extinguish this Class D metal fire. You'll see here in a second, things are going to go terribly wrong pretty quickly. Again, when we're not sure what we have, and we use the same old tried and true tactics, bad things can happen, and they can happen in a hurry. Turn the volume up here.
All right, we'll get 46s on that. Ben, you get a line. We've got other containers of titanium taking off right now. Hey, Dozer, you want us to take it around from the other side, around the... Everybody out!
So again, when they go bad, they can go bad in a hurry. Unfortunately, this particular incident from that explosion, they injured 6 or 7 firefighters, a couple critically. So again, when it goes wrong, it can go wrong in a hurry. So there's now a new chapter within NFPA 18A Chapter 9 that actually gives us the ability to test the water additive solution for Class D fire hazards. Up until the revision of NFPA 18A in January of last year, there was no protocol for testing any manual firefighting application on Class D metals. The only thing we had was UL 711, the fire extinguisher standard. So really a big breakthrough now in NFPA 18A. So this is that same customer at one of their other facilities. We're actually burning some titanium and zirconium here, using an extinguisher with a 3% solution. As you'll see, just like we saw with the other fires, a rapid extinguishment, particularly with the Class D metals, without any of that interaction, reaction you normally get. So the reason this is happening is we talk about that protective skin on the exterior of the water when the agent's mixed with water. So that we've now changed the substance on the surface of the water droplet from an H2O molecule to an encapsulating agent to an F500 molecule. That molecule is now protecting that water from that superheated burning material, from that superheated Class D metal, not letting that water split into hydrogen and oxygen. Because of the cooling capabilities, we can rapidly pull the heat out and rapidly suppress that fire. Another great example, this is magnesium. This is a magnesium fire. It's not going to play. Sorry about that. The link must be broke to that video. we'll go on from there. So let's look at the new up and coming hazard, the lithium ion batteries. And again, don't just focus on vehicle fires. These things are everywhere, both out in the public and right in our apparatus. There was just a post I saw on Facebook about 2 weeks ago. Fire department was working a structure fire with one of the new battery operated fans. Apparently the fan got pretty wet. I don't know whether it was a defective battery or what it was, but they loaded the fan back up in the compartment on the truck. And a couple hours later, the truck was burning in the station because the battery went into thermal runaway in the back compartment of the truck. So these aren't things we're going to face out on the street. We're running the risk right in our own stations. So again, NFPA 18A, if you look at the annex material, Annex 4.3 specifically addresses encapsulator agents conforming to Section 7.7, have been tested extensively and independently by third-party testing organizations, including Kiowa, Dacra, Daimler, Deutsch, Bosch, the Fraunhofer University, and TU Clausthal. Testing has been controlled and scientific, highly instrumented, documenting fire suppression, control, and elimination of thermal runaway. Again, the things can happen anywhere, and it's not just I don't know what happened, but the videos don't want to play. Idiot. Well, if at first they don't succeed, try again. Play the videos here for you. Have to find them. Give me a second here. Sorry about this. I don't know what happened that my computer quit playing the videos. You know what? We're in batteries. I got a better place to go. So what we're going to do here is look at some battery extinguishment of the burning batteries. This is of a prismatic pouch style battery. So they're using a overheating the battery with a heater, with a heat plug. You'll see the cell starts to swell. Starts to off gas. Agent discharges. So there were actually 3 or 4 cells in that pack. As you'll notice, the agent actually stopped that thermal propagation. So only the initial cell that went into thermal runaway is the only cell that burned. So again, rapid suppression of that fire without the propagation to the other cells. Another video here. This one was done at a testing lab over in Germany. So what we have here is 3 high definition cameras showing the battery setup. There's thermocouples set throughout the battery to monitor the temperature variations in the battery, as well as thermal imaging. So from the time the battery, they start the overheating process, you can see on the graphing the temperature's building. Battery goes into thermal runaway here in a second. We'll continue to allow that battery to burn for another couple minutes. Again, as you see, we're going to get temperatures here on your thermocouples are going to go up into the 600-700 degree range. See here as the agent starts to discharge onto the battery, how rapidly those temperatures drop. So we went from an excess of 600 degrees C to literally below 19 C. Temperatures aren't even being picked up by the thermocouplers any longer. Just that one application, they continue to allow the battery to sit. The agent continues to work, pulling the heat out of the battery, cooling that battery off. So let me go back to the slide presentation here. So unfortunately, we couldn't see that. So that's the video we just played. One of the things they were looking at during that video or during that testing, they were also monitoring the gases that were coming off the batteries when they were burning. What they found with the various style, both those polymer pouch and the 18650 style batteries, as those batteries were burning, they were giving off anywhere between 227 and 2600 parts per million of HF gas. That's some of the readings they picked up. But when the agent was used to start that extinguishment to extinguish those fires, those numbers dropped to anywhere from 1.25 to 37.5 parts per million. So again, a drastic reduction in the amount of toxic off gases coming off of those batteries when the agent is used to suppress those battery fires. We'll see if this one plays. I don't know what happened to this testing. That one I'll pull up because that one's a really great video. So this was, we did this with the New York, New Jersey Port Authority. So this battery is a, sorry about that. So this is a 48 cell battery out of a e-bike that they're using a propane torch to get that battery into thermal runaway. So hazmat applications, things like train derailments. So these photos come to us from down in South America, from Chile. This was a train derailment with a train carrying sulfuric acid. So this was coming from a mine. They use a lot of sulfuric acid in the mining industry in Chile. The tanker or the train derailed. the tanks released some of the sulfuric acid that was in the tanker cars. Here they actually used the F500 to encapsulate the diesel fuel that was coming out of the locomotive, as well as treating the sulfuric acid spill. So the testing that's been done with some of the hazmat groups in Chile, they found that using a 3% solution of F500, they can neutralize the sulfuric acid without having an exothermic reaction. So they can neutralize that acid spill, take it to a pH of about 7, again, without an exothermic reaction. Another tanker rollover, this one in Argentina. Again, they're using the F500 here to encapsulate the diesel fuel that has come out of the tanks. Another tanker accident, this one back in Chile again. So this is 2 tractor trailers, one rear-ended the other, causing it to spill the sulfuric acid it was hauling. Same thing. You can see here before they started applying the F500 that the sulfuric acid was starting to form a vapor cloud. See if this video plays. Sorry. They'll show you if the video would play, they're actually using that stream to neutralize the sulfuric acid spill. Last one here, this is a tanker rollover in Globe, Arizona. This was a gasoline tanker that went down over an embankment. I'm assuming these videos won't play either. Let me see if I can find that Globe video to actually show you the videos separately. That's why I like to save everything. Tanker spill. Hopefully they'll play inside this one. Let's see if I can get this other PowerPoint to open, if we can get the videos to play in there. Love it when a plan comes together. Well, here, let's go back. So here you can see, oh, sorry about that. So they put some guys down, they were doing some monitoring, put some folks down over the embankment to actually strap the truck and drain the fuel out. And they were using a 3% solution of F500 to both treat the fuel that was spilled out of the truck, as well as keep the vapors down to prevent an explosive atmosphere as they lifted the truck back up onto the highway. I apologize for the technical difficulties today. I'm not sure what happened. We'll get to the end of the presentation here. We're almost through. So if we look at everything we talked about today, you know, F500 is one agent. They can work across multiple applications. Helps take the guesswork out of what do we need to use for the hazard we're facing, especially if it's an unknown hazard. You know, are there batteries involved? Is there Class D metal involved? You know, can it make it a safer environment for us to walk in? So again, you get the encapsulation benefits, encapsulating that hydrocarbon, rendering it non-flammable, that rapid heat reduction, the calorie absorption gives you a great burn back resistance, that free radical interruption, which improves the IDLH atmosphere and makes it safer for everybody, all in an eco-friendly, fluorine-free, biodegradable, non-corrosive package. when you compare it to some of the other things out there that we're using, you know, with plain water, we don't really get a surface tension reduction. And while it removes heat, it's really inefficient for the volume of water that we use. Very little of it actually turns to heat, or turns to steam, excuse me, to absorb heat. When we look at an NFPA 11 foam, it helps reduce the surface tension so that it can absorb in a little better, but it forms a blanket to separate that fuel from the oxygen, and it's really good at making blankets. But again, think about if you're cold at night, what do? You pull a blanket up. Those blankets help retain heat. It's one of the reasons we need to keep continually applying a foam until that surrounding material cools to the point where once the blanket breaks down, it won't auto-ignite that fuel. If we look at wetting agents, they reduce surface tension, but they really don't do anything to reduce the heat. When we look at an encapsulating agent, you get surface tension reduction, you get encapsulation, you get the rapid heat reduction, and the free radical interruption, which improves the IDLH. So again, working on that entire tetrahedron simultaneously. That's it for the presentation. I'll open it up to questions. I thank everybody for your participation. Great questions. I hope you found it informative. Looking forward to the next one. You know, again, more questions, please. info@hct-world.com. You know, we're more than happy to get you any information you're looking for. Any other questions that you think of after the fact. Love the interaction. Love spreading the information and the knowledge about the agent, how we can hopefully make the fire service a safer service. Thanks, everyone.